Hey there, everyone. It's good to see you, or at least for you to be able to see me. My name is Robert Bruce. I'm a research scientist and chemist with Virginia Tech. I'm very grateful to be able to talk about some of the work that I do, which focuses on light and how it interacts with different objects. But before I go any further, I just want to share that just like you, I'm a Science Olympiad competitor. Well, at least I was back in high school a few years ago. Back in high school, I took every form of chemistry event that I could get my hands on. Chem lab, which is a staple nowadays, food science I took. We had this event where we had a case of unknown powders that we had to identify, put together synthesis and identify them. It was all really cool, and I'm grateful for the experience. It helped me to become a scientist today. Like I said, today I'm going to focus on talking about some of what I do, but I also want the focus to be a bit of a talk of inspiration. My talk is titled Seeing Eye to Eye, and it actually focuses on talking about moth eyes, because there's an amazing story of how scientists took images of a moth eye, something that seems rather benign when we talk about it, and how that led to a revolution in light and how it interacts with surfaces and how we use it for many, many different purposes. Ultimately, though, I want the focus of today's talk to be surrounding one question. Where do we find inspiration? Where do we find the important questions to ask? Or where do we find the answers to our questions once we have them? Our virtual worlds taught us that Google is a great source of information. And in fact, that's the one image I've left off with this slide of where we find inspiration. There's many other places as well. We can find it through math, through observing. I want to talk about a more organic source of inspiration today, that source simply being nature. Here's the case study I want to build. Like I said, my work focuses on light and how to manipulate it. You probably know from the world around that there are some basic rules for how light interacts with different materials. We know light reflects off some surfaces, it transmits through others. It even changes direction when transmitting from one material to other, such as from air to water. More often than not, it does a combination of all of these. Think about when you look outside a window in your house. You can both see out the window, you can see reflections of the room you're in, and the image is sometimes distorted or discolored because light interacts with the window itself. The technical term for all these is transmission, reflection, and refraction. They all happen simultaneously, and it's a basic principle of light that these happen simultaneously in all cases. We might not care that all these happen when we look outside the window, because the window does a good enough job, but there are situations where we do care. Think about your glasses. You can already see that there's light reflecting off the glasses, and frankly, we don't want that. It means that there's light that doesn't get through to your eye. It also means that you can have a bright spot on your glasses that keeps you from seeing. And that's a very down-to-earth example, literally. Let's think about something where light's even more critical, something like the Hubble telescope. It's a billion-dollar tool that's designed to observe images from literally across the universe. You don't get much signal from that far away, so every photon it receives counts. And you can't have precious photons just reflecting back into the vacuum that's space. The ideal surface for the jobs that I'm talking about is what's called anti-reflective. So we put anti-reflective coatings on things like glasses and Hubble telescope optics, which help them reflect less and function better. We have possible solutions to the problem, but they're often expensive and can be tough to implement. So let's seek some inspiration and try to see if there's a different way to do it. Let's ask the question, where do we find inspiration for this? And in that question, let's ask, how does nature do it? The human approach is to coat surfaces, but nature doesn't have the fancy tools that we have to coat and deposit materials. It does things naturally. So how does it happen there? In seeking inspiration, much like your glasses, we can identify cases where anti-reflective properties are important. For example, nighttime. So little light exists that nocturnal creatures need to capture every photon of light so they can see around them. And just as important, many creatures will get seen if light gets reflected back to predators. Let's cue the humble moth, the often unwanted groupie at every nighttime party that you've ever shown. Scientists ask the question, how is it that moths are able to see at night so well? So they took some images basically of some moths and found something rather extraordinary. What you can see in this image is a very zoomed in image of a moth's eye, so zoomed in that we're talking on the right side that it's literally thousandths of your fingernail. When you actually zoom into the size, you see something that's absolutely crazy. On the left, you already see that there's some texture to the moth's eye, But then we zoom in on the right and zoom in much, much further, and we see that there's nanostructures present naturally in the moth's eye. Scientists studied this for a while, and they found that this helps give anti-reflective properties to the moth's eye, helping it to see better at night and also helping it from being able to be seen by predators. It's a crazy outcome to a very real problem. And more importantly, it provides inspiration to scientists about crazy new ways to control light. One other image I'm going to show from the other end of the spectrum, moth's eyes worry about reflecting light, worry about minimizing reflection of light. But what about cases where we do want to reflect light? Nature does this in a lot of different ways, but that same nanostructure approach comes up when we talk about certain butterflies. These butterfly wings, we know in some cases, are very vibrant, very colorful. And when we zoom in on those wings as well, we can find that there are nanostructures present on butterfly wings. Again, in this case, it actually generates reflection and only specific wavelengths of light, because we see that those butterfly wings are colored. They're very vibrant as well. So we get a phenomenon called iridescence, or bright reflective colors in the wings. Between the two cases, nature's given us some really amazing thoughts here. We see that, again, moths can prevent reflection of light through nanostructures. Butterflies can create it through nanostructures. They contrast in function, but it leaves one question. Can't we use nanostructures to control light on surfaces? And this is where I come in. What I do is I create nanostructures on surfaces to manipulate light. I'm going to bring up an image of just what I do here real quick. But what I do is actually a very simple approach. I take a surface and I dig holes. These holes are obviously of particular size and of particular orientation, but at its core, it just boils down to taking the surface of a sample, imprinting it with some holes or etching materials, just a few thousandths of your fingernail deep again, and then we put patterns into it. The result of even this small application is simply called exquisite. Again, it opens up many, many new possibilities for how light interacts with surfaces. I'm actually going to try to show you a few examples of what I've been able to do. So give me a second, let me get set up. I have two wafers to show you. I'm literally just putting on gloves. But like I said, all we need to do is just take surfaces and put holes in them, just a little bit deep. What happens when you do that is you get objects that are very, very reflective, very colorful. Obviously, right here, I'm pandering to the audience by showing a Science Olympiad logo. What you can notice, this surface is naturally very reflective. By putting these air holes, these holes of particular size, distance, and depth, we can start to reflect light. This is actually really interesting because the light that's reflected you see is dynamic. It depends on the angle at which you view it and the incident angle of the light. So I'm doing my best to show you over camera, but it's really, really cool to see in person. And I have one more to show because that's a very simple example. All of those are the same air hole size. But what if we start manipulating the different sizes of the air holes? And what you can ultimately get is something that's really, really interesting. This, hopefully you can see, is an image of Starry Night by Vincent van Gogh. My apologies, I'm doing the best I can to represent it. Again, you can see that it depends on the angle and the reflection off of it, but it's really exquisite to behold. Simply by changing the air hole sizes, their distance, just a little bit from each other, you manipulate how light interacts with the surface, and you get these dramatic colors that just change over time. This is a very basic example, and obviously just a novel one, but it's one example of how we can use these holes, these simple nanostructures on surfaces, in order to be able to get something much, much more dramatic out of it. Obviously, scientists go much further with this. As soon as I get back to my slide, I can show you just some, even what I would call simple patterns that scientists do simply by changing the size, the shape of these features. The applications of this type of science go just anywhere your imagination wants to go. We can manipulate images, obviously, off of these nanostructures. We can project images. You see on the right, that's actually an optical image that these nanostructures do. It's literally opened up a whole different field with many, many applications to it. I mentioned anti-reflective surfaces. There's just a whole boatload of applications that come from this. Just some off the top of my head, we have retroreflectors, which reflect light back in the same direction they come from. You can make basically transparent materials and start to focus on invisibility and generating that with surfaces. You can create magnetism without magnets. It's completely bizarre how you can do this, but it's also amazing that you can manipulate surfaces in what I would call the simplest of ways and generate so much control of light from it. Obviously could go on for a while, but I think it's fair to say this nanostructure-based approach to optics is a revolution in our thinking and understanding of light and how we control it. We spent a few minutes now in more of a technical conversation. Let's bring it back down and talk about how we got here. We asked a question, how do we control light? We sought inspiration, we looked to the moth. In seeking inspiration, we asked another question, how does the moth do it? Or how do butterflies do it? How does nature do it? Then we looked and found those two cases, and we looked at them really, really closely. We dug down until we had a possibility of how it manipulated it. And then we applied what nature gave us, not only recreated on it, but we were able to expand on it to many, many different applications. I want to close out by focusing on this inspiration and how to find it. I've obviously given one case study, but when we think about the stereotypical images of scientists, there's a lot of kind of what I talked about here. I think a lot of these images involve somebody looking. A biologist looks through a microscope, a physicist looks at numbers and readouts on a tool. Chemists tend to get a bad rap because that stereotypical image is staring at a beaker, but I assure you, we do a lot of looking, reading, learning as well. And scientists, researchers, engineers in any field are all incredibly smart people, but we'd be foolish to think that our knowledge set is all that we need. We have to look. So what we do is look. We spend a whole lot of our time just looking. And it's that looking that we find our inspiration and are able to solve some of the most amazing problems in front of us. The amazing and terrible thing to this is that there's really no formula to where to look for inspiration. As we talked about today, nature ended up being a great source for how to manipulate light on surfaces. I do encourage you to look to nature because I could talk for another long while about how nature has inspired a lot of scientific revolutions. But in any case, I hope you open yourself up to finding inspiration in what might seem the most unlikely of places. Ask questions. Don't be afraid to go down different pathways to find answers to those questions, even if the first ones end up at dead ends. The problems we seek to resolve in research are complex. They'll require us to learn things we didn't think relevant and to talk to people outside of our comfort zones. But most importantly, they're going to require us to have an open mind. If we do this, if we have this open mind, open ourselves up to talking to people about moth eyes in some cases, the rewards to the process can be extravagant. I can't promise this process is easy. It'll take time, it'll take effort. Many of you know this simply from Science Olympiad. It takes time and effort to learn new things. And it takes time asking questions that maybe don't end up as fruitful to start, but then you find the ones that are. But when you give that time, that energy, that willingness to let yourself to get past the stage of this is different, a closer look might make you realize that two different ideas might actually be able to see each other eye to eye. With that bad pun, I want to thank you all so much for listening. I hope that you, all our competitors, do amazingly at the national tournament. And just thank you to Science Olympiad and the national tournament for the chance to get to talk with you today. Good luck, everyone, and take care.